My name is Helen Lurie, and I design radios and electronics for a really tiny spacecraft. And, huh? What?
How tiny is tiny?
Oh, how tiny? Well, you're basically limited by some aspect of responsibility to other people in space, which is as long as you can be power positive and can control your satellite enough to avoid collisions, you can make it arbitrarily small aside from that, as long as those constraints are met. I typically work in what's called the CubeSat environment, which is about 30 centimeters by 10 by 10. And then unfurlable solar panels will make it more like a meter across. But in package form, it's about a bread box, smaller. Okay, so why space? It's got a really good location, and location is everything here. There's a lot of applications. For geo, you do broadcast, because broadcasting radio signals from space is actually cheaper than digging up all the dirt in Canada and running fiber all across all that lone tundra all over the place. So instead, you just put one geo bird up, which is kind of crazy. Think about it, that $1 billion is cheaper than that. But yeah, digging dirt is really expensive. Internet for ships, the Arctic, MEO, it's a little bit closer. I'll have a plot of the distances from the Earth, but that's medium Earth orbit. It's a little bit below GEO. Again, you still do communications from that. You can do space physics, and the GPS satellites are up there, which we all use. And LEO is mostly the playground where I play in. And there's a lot of things about LEO that make it easier to start innovating in it and to start doing low-cost manufacturing techniques that you can't quite get away with in GEO. Again, communications, spying on people on the Earth. I don't work for any sort of military, so I don't spy on people. Earth exploration, ship tracking, plane tracking, like the recent Malaysia airplane that went down. There were satellites that were listening to those signals, for example. Laser comms research, photography. So this is a little bit small to see, but I think we can do this. Do you see the Earth? And right next to it is the little blue line. That's where LEO is. So it's really, really close to Earth. And then green is MEO. You want a pointer? No, I think we can just do colors. And GEO, or if you have one, I can do it. That might help. No, you don't have it? I thought I had it. Okay. That's fine. I can just point and just flail my hands wildly at the screen. Ah, schmancy. Thank you. Oh, let's see. Ah, look at that. Okay. And GEO is really, really far away. It's actually off this chart a little bit. It's 35,000 kilometers away. So being up there's a lot of constraints, like the space environment. Stuff is really, really far away. So there's signal latency issues. So normal TCP/IP won't work if you're trying to connect up to your satellite, because one side is waiting for an ACK and the other side hasn't even gotten the packet yet before you time out. The other big thing is, like, you have no physical access to it. So if you push a software bootload to your satellite and it causes the default state of your satellite to go into like a non-listening mode, you have lost contact and you will never regain contact again. You cannot set an intern to go flip switch in the server. So whatever you do, whenever you do a design technique, you always have to have a safe state that the satellite will go back to if it hasn't heard from anybody in a while. Vacuum. You get things like multipaction. Fans don't work well for cooling. It's like everything's covered in a down blanket. And solder whiskering. So multipaction is kind of a fun thing. We don't really run into it in LEO, but when you have a big waveguide and you have photons or electric fields, however you want to think about the universe, going down this thing. If there are certain power levels that are strong enough and the frequencies of oscillation of the signals match up with the dimensions of the waveguide just right, then as the electric field energizes electrons on the top side of the waveguide and causes them to shoot out, they'll reach the bottom just about the time that the potential energy is flipped the other way. These electrons get ejected also. So you get this rising wave of electrons going back and forth and welding the waveguide shut or damaging it in some way. If any of the conditions are not met, like your signal's not strong enough or your waveguide's not quite the right size for this to happen, it won't. We don't have to worry about this in Leo because we don't tend to run like 60-watt traveling wave tube amplifiers like they do at Laurel. So what else? You always want to use leaded solder. It's a little bit better for a lot of things. Solder won't whisker as much if it's got lead in it. And so this actually runs into using off-the-shelf chips because they all tend to be COTS compliant. Not COTS or COHT, whatever the lead compliance. Temperature changes. Your satellite will go through -25 to +50 degrees, and this depends on your orbit, this depends on the time of year, this depends on your size. But in Leo, we see these kinds of temperatures. In Geo, they can be more extreme. Practical thing is you want to use TCXOs, temperature compensated crystal oscillators, instead of just an oscillator for your clock. A geostationary satellite, we use an ovenized crystal. So that's like a big box that's constantly keeping the entire crystal at warmer than it would ever get to naturally, and so it can always keep it from getting colder. There's a lot of problems with using ovenized crystals. First of all, they tend to be like this big, or you can get them a little bit smaller. And the other thing is they take a long time to warm up, and while they're actively warming, the crystal's frequency is drifting all over the place, and so that means your radio center frequency is drifting all over the place. So that means you have to keep them on all the time. In Leo, we can't afford the power. So we cut corners. This is the first corner we're cutting, TCXOs, and they're good enough, and they're not too expensive. You want to test everything on a thermal oven, so you cycle it, preferably a thermal vacuum oven, so that your spacecraft will actually experience the vacuum, and so heat buildup will happen as expected. Debris. Occasionally your satellite runs into things at 3 kilometers per second, or your satellite will either its fault or somebody else's fault. Maybe it's a piece of debris. Maybe your satellite's lost control. You tend to sign up for these Air Force email announcements. There's a government entity that tracks every single object bigger than, like, I don't know, a postage stamp or a couple of postage stamps up there. And you'll get these email alerts, and I've gotten them a few times. They're quite worrisome, like, you know, dear so-and-so, you are registered as an administrator of object da-da-da-da-da. You know, you are imminent for an upcoming collision in, 1 week with this other object. And so then you get on the phones and you start scrambling, calling the other operator and seeing who's going to steer out of the way if it's looking like it's still going to happen. So there's a lot of radiation up there also, and particles flying all over the place. Leo is a lot easier than Geo. You tend to be protected very strongly. You're closer to the Earth, and you have convenient magnetic fields that are deflecting a lot of crap that you don't want hitting your electronics. And so we can cut corners because we're closer to Earth that you can't do in Geo. So some parts of this talk are not exactly applicable to doing low-cost engineering up there. There's a lot of regulations, ITU, NOAA, FCC, everybody wants a piece of the pie. So NOAA cares about debris. So if your satellite, when it breaks apart upon reentry, is going to actually hit with a big chunk somebody, you need to register that. Basically, you need to get a license showing that your satellite will burn up, that you've done the analysis as you're going through the atmosphere. The FCC, they care about frequency allocation. If everybody just grabbed however much bandwidth or frequency they wanted all the time, then there would be none left over. At least that's the theory. So you have to register in advance and pay huge bonds and filing fees in order to be able to operate. Anybody can reach your satellite via radio. The bandwidths and the center frequencies are all public knowledge. So if you don't secure your link, somebody's going to figure out what your modulation scheme is, and they're going to crack it open if they want, or start bouncing signals off of it. We've seen that happen already. People just commandeering other people's transponder channels. On the other hand, space is easy. Users can't drop your satellite into a toilet. There's no dogs or kittens chewing on your electronics. No security vulnerabilities due to physical access, no humidity, and there's very little atmosphere, so stuff doesn't rust, and there's very low drag. There's not a lot of RF attenuation. The entire time the signal is propagating until it hits the atmosphere, it's only doing the range loss due to the electric fields spreading, but it's not actually being, hitting water molecules and oscillating and transferring energy to them or scattering, which is what signals on, the planet's surface do. And so this is actually quite interesting because we can use Texas Instruments' little ISM band chips that are rated for, if you're actually doing like WiMAX or Wi-Fi or something like that on them, they're rated for like, I don't know, 50 meters, 100 meters. And all of a sudden you put a power amplifier in front of them and you try to talk to space, and you can, because the S-band radiation isn't busy heating up the air all along the way. And bouncing off of things, and these kind of environments are really complex to deal with for electronics because there's EMI and signals bouncing all over the place. Up there, it's pretty quiet. You can get a lot of sun, and your solar panels don't get covered in dust. In Los Angeles, you look at a solar panel, we put them up on the roof of SpaceX, and these things were producing basically no power at all after a few months because they had gotten caked with like a thing of this greasy grime that you could just run your finger on and just pick up palpable, disgusting black goop, just Hawthorne air pollution. Up there, solar panels stay pretty pristine. And you don't have to cut corners on every 5 cents of your design. When you're designing an iPhone, you can bet that they care about every 5 cents. For space, you start cutting corners on every $50, or if you're building a GeoBird, maybe you start cutting corners on every $400, but you don't have to worry about 5 cents. If you want to buy a nicer capacitor that costs like, 8 extra cents off of DigiKey, it's okay. You can splurge.
So you left off 0G, and I think the security vulnerabilities question, that's only a temporal thing right now, probably.
That's true.
Because certainly the Soviets did actually look seriously at weaponization of their various spacecraft. Mm-hmm. But I'm surprised
So do we.
left off 0G. Well, not to the degree that the Soviets did, though.
Yeah, so 0G in a lot of ways helps. One example is you can get away with using springs that are a little bit too weak. Like if you try to deploy your small solar arrays on the Earth, down here they'll be kind of saggy a little bit, but up there they won't. They'll be nice and straight. And so things like that. So.
The satellite that I launched.
Hey.
No, let me finish. The satellite I launched, I had one of my bosses he was hoping that it was going to blow up on the launch pad because we were flying the largest antenna ever flown in space.
And it fills that end.
It's more than that. Go ahead though.
Okay. Right, next. So how do you get to space? By adding a lot of megajoules of energy, both potential and kinetic. And rockets are pretty expensive. If you're trying to get to LEO, you're looking to shell, at least 10K per kilogram. And GEO, it's more like 27K per kilogram. And so this leads to some fun engineering. Replacing every 1/4" 20 steel bolt with titanium saves you $50 per bolt to LEO. Because the bolt increases in price. I have the exact numbers here. Here you go. It's $150 to launch a single bolt, but you cut the weight in half, but titanium costs more, so you end up saving 50. So you can do the math there. And rockets are pretty harsh environments to be on. You have vibration, shock, and acoustic. We'd find these dead coconut crabs on Omelek after every Falcon 1 launch, killed by the acoustic wave coming off of the rocket as it lifts off, and because the engines are on. How do you grab a rocket? You're a small person. You're trying to do small LEO satellites. You can't just like call up SpaceX and go, "I'd like a Falcon 9 now." If you are, Intelsat and you're putting up a big GeoBird, you can just commission an entire launch vehicle, which means you have bought the ride completely. You control where it goes. You have prime, mechanical considerations, everything for you. But that costs a lot of money, and you have to pay a lot of insurance to get up there. So riding as a secondary opens up opportunities for low-cost satellite builders. Let me just check the time, 4:36. Okay. There's a lot of entities like the University of Toronto and ISIS that are organizing launches for you as a secondary. So if you have a small satellite, maybe yay or maybe yay big, they'll find another launch where there's room inside of the fairing. So the primary is in there, and they've already seated it mechanically, but there's all this room along the edges. And so after the primary is ejected, there's these secondaries living in these things called P-pods. I'll show you a P-pod later, that are ready to deploy later. Oh, test flights of new rockets are another good thing. I remember on Falcon 1, Flight 3, we killed, I think, some number of student CubeSats that were hoping to get to space cheap on that launch, but unfortunately it failed. There's different ways of solving the constraints. So for Loral, which is one example of sort of old, reliable, traditional space, satellites cost several hundreds of millions. Sorry. And because of this huge price tag, and because of the huge market that's behind it, by the way, somebody who's willing to shell out this much money for a satellite has a huge billion-dollar market behind them. There's a ratcheting process on the cost and the amount of testing. Well, it's like, well, because every satellite costs so much, might as well spend $500 on a harness, on just the connector for a harness to make it super, EMI wonderful. And because the customers already spent so much, they're going to push you as hard as they can to do another test to chase down 0.3 decibels of power difference here or there. So they're going to stop the entire operation, backtrack, and you have to reset up everything and test to find these measly, measly small amounts. But it's important to them because there's so much money riding on the situation. The development cycle is pretty old. And ordering parts, if you're trying to be a small person entering this field, is basically impossible. Ordering these traveling wave tube amplifiers that they're using, like the lead times are long, the costs are huge, and you can't just buy one. So,
so is that for high energy transmission? Is that why you need such expensive amplifiers, or why are there such?
It's a couple of things. One, they're super reliable. The stuff that you buy that's like rated for geostationary satellites is bulletproof. It will never fail from radiation. It's got all these, checksums and fault tolerances on the inside. The cases are like thick, thick, thick milled metal. They're sealed off and gasketized completely. The workmanship on these things is fantastic. They will last in space for about 20 years. And yes, the energies, because you're so far away from Earth, you need really, really high radio signal powers in order to actually reach your users or reach the ground station. And because the costs are so high, you often don't have an engineering unit. So you're trying to debug your satellite, which isn't working, and you sometimes don't have access to an engineering unit that you can just like tinker around with and take apart with a saw and resolder a new inductor on it to try to figure out what's happening. You're just trying to debug it kind of in the air. And maybe if you get your hands on an engineering unit, you can't destroy it because it's probably the only one. SpaceX did things a little bit differently. Rockets cost a lot less money there. The development cycle is really, really short. These people are changing Falcon 9 every time it launches. They have never launched the same rocket twice. It is always going through revisions. I don't know if every time, but that is just the company culture, is to change and innovate every single time. And ordering parts is, you just kind of get on the phone with your vendor. It's like delivery time is about 2 months after receipt of order, and you have an extra couple of units lying around on your lab bench that are for destruction and testing. So it's a lot easier to innovate quickly in an environment like that. And then there's AltSpace, which is the CubeSat world. This is like Planet Labs and NanoSatisfy, both up in the city. This is Canopus Systems over at NASA Ames. Again, the development time is really short. You get your chips on order from DigiKey. You just use a $10 Molex flat mount connector. Ribbon cables are your friends. You get your PCBs printed at Sierra Proto Express in Sunnyvale, and they come back to you in about a week. You assemble them all by hand. A set of flight boards costs you about 1.5K. I can break down the cost, and I will later, but roughly, getting high-frequency RF material printed on a PCB for a run of 16 boards is going to cost you under $3,000. That's just for the PCBs. And then the parts to populate all 16 of those are going to cost you another, I don't know, $4,000, $5,000 in chips, maybe less. So you're looking at the whole thing is like $8,000 plus assembly, and you have 16 radios out of that. Because they're so cheap, you basically have like 6 engineering units for every single launch just lying around on the table, and you're taking these things apart, and you have a soldering iron. And we used to have at Planet Labs what was called the electronics cemetery up on the wall. And so there'd be, so it's that electronics cemetery, and then there was all these ESD bags with the dead electronics in question and the cause of death written on a little Post-it note with its name and the serial number stapled up there. So people go like, how did we break that X-band transceiver? Let's go pull it off. Oh yeah, I remember the cause of death is written right here on the Post-it note, and the board's right there. You can take it out and re-examine what is it that you did wrong last time. And it's also kind of a joke, also alluding to the fact that it's okay to just fry stuff and destroy stuff. Like there's like smokes and curses coming from people's lab benches all the time, and it's okay because stuff doesn't cost a lot. And at least in the companies I've experienced here, you continue to rev the boards constantly and you launch what you've got. This is what most of these people in this field are doing. They're just continuously revisioning. So why can we do low-cost satellites now? Let me check the time really quick, 4:40, okay. Oh, look at that. I don't even have to tell everybody what like my mental state is. I just glance up there all subtle like, thank you. All right, so what led to the low-cost satellite revolution? Part of it was the invention of the CubeSat bus format and the invention of the P-pod, which is a standardized deployer for small satellites. Let me jump ahead really quick to show you a P-pod. This is a 3U CubeSat deployer. 3U is you know how in racks there's a 1U rack unit, which is like 1.5 inches tall, 28 inches across or whatever. In satellite speak, this is a 10 centimeter by 10 centimeter by 10 centimeter block, at least when it's folded up. You can have whatever you want unfurl from it, antennas and solar panels later, but when it's on the launch site, it must fit into a third of this. That's a 1U unit. You can have a 2U satellite. You can have a 3U. You can have any combination of those things between different clients all running together in the same deployer, and they'll just get spun out in order. This lid pops open, and there's a spring down here on a piece of metal, basically, and it just shoves. And there's latches on the inside that keep satellites from breaking out until it's their turn. So if you have 3 different satellites, the second one will have a latch holding it in place even when the first one's being pushed out after the door opens. And then that latch burns and it goes out. Also, Moore's Law really helped. Even though $10,000 per kilogram is still a lot, Moore's Law says you can do a lot more with 1 kilogram than you could do with 1 kilogram 20 years ago. The computational speed you can have up there, the digital cameras, the radio chips, it's amazing how easy and simple and fast stuff is to develop now. Higher precision manufacturing leads to more radiation-tolerant components, but there's a huge caveat here, which is the junction sizes are getting smaller, and that actually makes things more susceptible. On the other hand, because they weigh a lot less and they're a lot smaller, you can afford to spend more volume and space shielding them. And various groups have done studies of how much shielding do you need in LEO. And if you're looking for about a 2-year orbit, because probably in 2 years Moore's law has made your current satellite obsolete, so you might as well replace it because it's all fairly inexpensive. Also, you're decaying quite a bit more rapidly in LEO. There is a little bit of atmosphere, so your satellite is still hitting the occasional speck of air here and there and here and there, which is slowing it down. So if you want about a 2-year lifespan, you need about 3 millimeters of aluminium shielding. That's not a lot. It's not terrible. If you have that all along the outside, the stuff on the inside is reasonably tolerant. It'll still get occasional upsets, so you still need to have watchdogs monitoring the state of your components and flipping power on them back and forth if they don't reply. But they probably won't have horrible, horrible damage in under 2 years.
Can you apply Moore's law to the satellite? All of the nanosets?
Well, we're trying.
Nanolight seconds, like.
Well, we are trying, and it does work that way, actually. Like, here's an example. I remember worrying so much about mechanical strength for the big components I was integrating at SpaceX, right? Because everything is always going to be on a rocket. It's always being shooken and sloshed, and it's cold or it's hot, and it's not a very comfortable place. Goldilocks would refuse to ride up there. But we had to worry about things, all their torque moments and how they're going to crack this way or another way. Satellites, when they're really, really, really small and you're designing the PCBs and you don't have heavy, vacuum tubes on them, causing a whole bunch of mass to be sloshing around, and all you have is a teeny tiny chip, it makes the mechanical integration a lot easier because your PCB has no weight on it. It's probably not going to break as long as it's in a good frame.
So do you radiation test all your electronics on an ongoing basis, or?
You should.
But you don't.
But we don't. You kind of just do it on orbit, but you can, and there are entities that do. And one useful way of doing it is if you have access to a particle collider, great. So if you know of a research institute that has one, you can accelerate particles up to the correct energies and hit your boards with it. There's a pretty good easy cheat, which is that there are irradiation facilities located anywhere where there's dairy farms. The closest ones around here are in Gilroy. And they have a cobalt-60 source, which basically, it's a big chamber, and inside of the big chamber there's a smaller chamber, and inside of the small chamber there's a mechanical deployment mechanism where the cobalt-60 can hide inside of the inner leaded chamber. Meanwhile, you wheel in your big racks stacked with eggs or milk or whatever it is that you want to fry, and you tuck them in there, close the outer door, and then the cobalt-60 comes out. You can do the same thing for satellites. You can basically rent out one of these chambers for a couple of night times on their off shift and pop your satellite in there. It doesn't give you quite the same distribution of energies that you'd like, and it's not all the different kinds of particles, but it'll give you some idea. That's an inexpensive way, and again, a particle accelerator will give you the complete spread of all the different types of, nuclei and photons and whatever else that you want. Yes, I think we covered that slide. There's the Peapod again, the lovely Peapod. So I've built mostly satellites which take this whole thing up. Yeah, but you can build smaller. This is what 3 CubeSats look popping out of a Peapod deployer. So you can see it's 1, 2, 3, one after the other. These were released by the International Space Station fairly recently, a few months ago or in last year sometime. Fairly pretty picture. It looks like these guys, either they don't have any sort of deployable solar panels. You can see they're lined with solar panels on the outside. Or maybe the people on the ground will wait to give signals to deploy things later on when they're a little bit more spread out from each other, because you can see they're pretty close right now, like about 15 centimeters apart. So what is the state-of-the-art nanosatellite? What are we doing there? This is a picture of a recent Planet Labs launch coming out of the deployer, again on the International Space Station. These are 3U So they were inside of a Peapod style deployer in here, and you can see that the lid popped up already on this one. It was just being held up there by that lid being closed, and so it already has something deployed. But more stuff will come out later. So this is a picture of a whole bunch. I guess the photograph's pretty artistic and close in, but it's a picture of a whole bunch of them. They just have, 30 or 40 satellites lying out on the lab bench. So if you really need to test one, you just grab one, mark it as an engineering unit now, not for human consumption or not for launch, and just start playing with it. Most everything was developed in-house there. And we made everything happen to the time of the first launch in under 2 years, from design, iteration, and to the first huge flock launching earlier this year. This is a picture that Steve of, DFW, whatever that VC firm that backed Planet Labs took of us. You guys recognize this here. This is the dish on top of the hill. And I was the operator for this, and so first a couple of satellites were just coming up. We had no idea if they were going to work, but we just, powered on the dish, and we had our radios there, and we managed to reach our satellites okay, and everything worked. This dish, by the way, is awful to operate. Has anybody here had to steer this thing? It's horrible. If you you give it... Huh? It's not only ancient, but it's like some sort of old missile turret or anti-missile gun or something. Yeah, we once accidentally entered so you enter these configuration files for this dish that have like a time step and then the new azimuth and elevation, time step, new azimuth, new elevation. And the software, which runs in DOS on this thing, doesn't quite check the coordinates. So if you happen to maybe reach the end of the file and not have the correct end of file delimiter in there or something, and it tries to go back in one time step to the beginning, it will try. And because it used to be like some sort of huge anti-military missile gun, this whole thing just starts... It's scary how fast this thing can accelerate and turn. It's insane. So I remember having to go like, exit, 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 stop, when that happened. Huh?
With the hand on the circuit breaker.
Yes. So this is a picture that we got down from space at Planet Labs using the high data rate X-band radio that I designed, all in-house. And we were able to transfer fairly high resolution images down, a lot of them also. I can't tell you exact data rates. Or can I? Is that on the FCC application? If you're interested, go check the FCC application. Whatever is public knowledge about them, you can find there. So what are some rules for building state-of-the-art space radios, or really any sort of electronics? It really helps that you are so inexperienced that you don't know X-band doesn't fit inside of a CubeSat. It really helps that you don't know what's not possible, because I didn't know it was impossible, and so therefore it worked. My manager at Planet Labs very carefully did not tell me that when he was at a conference, somebody said, what you guys are trying to do X-band communications in CubeSat, that'll never work. And so he just did not relay that over to me, and so I didn't know. You just use off-the-shelf chips from DigiKey. There are companies that are making amazing transceiver modules and power amplifiers that are just teeny tiny surface mount chips. You can just get them stocked off of DigiKey. There's companies like Analog and Texas Instruments and Linear and Hittite that are just doing amazing stuff all the way up to K-band. If you use software-defined front ends, then you can continue to leverage new packet protocols and forward error correction schemes as they come out. And so you don't have to relaunch a new satellite in order to gain new software functionality. But again, back to the proximity issue, you need to make sure that whenever you push a new software image up to your satellite, that it's not going to break the current behavior. So you always have to have some safe state. But you can push something up, put it into another memory slot, you're in the safe state, and then you try the new software image. If it works, then you keep it. If it doesn't, you just go back to the safe state and report that to the ground. Let's see.
So what kind of operating system do you run in those satellites?
I can't tell you exactly what any particular company is doing. But you want a fairly real-time, robust operating system that developers that you pull off the streets in San Francisco know how to develop for.
Wind River.
Sure.
Most of them use Wind River.
The X is the product.
Yeah.
Almost uniformly, people choose Linux. As to what particular flavor, you have to do your research, but that is a very good OS. It's not completely real time, but it's better than Windows. Anyway, you don't want to be running Windows in space. That would just be a really scary thing to do. Let's see. I'll go into the modularity. Okay, so I actually wanted to go into Eagle right now and show you guys the radios we're currently designing for BitBeam Technologies. This is the Gerber files for it. We are leveraging off-the-shelf chips from Texas Instruments to use as the transceivers. These are ISM band transceiver units, so they receive and send. They're running 805.1 microcontrollers on the inside, and it's all integrated with the RF circuitry. All we have to add to the front of that is, so for fault tolerance here, basically, we've placed a high data rate MCU that can talk up to 2 megabit per second in speed, and a low data rate MCU. And everything is broken out to these connectors, which basically bring the USB out to the flight computer. And here, if one of your MCUs goes down, either permanent damage due to radiation or something else, where it won't power up, you can just switch over to the other one. And also, you have the two different ones for different data rates. They overlap over some range of speeds. And we had to add a front end. This is a chip from Avago. It's a 2.5 watt power amplifier. This is a driver amplifier for it. This is the footprint for a Faraday cage to shield the front end because you don't want stray photons getting in there from the rest of your electronics. USB, by the way, is really, really noisy. That stuff radiates all over the place. Like there are, all the USB chip manufacturers, they all have FCC rules that they have to abide by. And I guess whatever those rules are, they're fairly loose by my standards. They work for a computer case or for a laptop, but like they're awful when you're trying to operate in a nanosatellite where like the next PCB is like a centimeter away from those USB lines. And so to prevent that kind of stuff in a really small format, we use a 6-layer stack up. The top layer is a high-frequency RF material. The bottom layers are all FR4 because A, it's cheap, and B, it's structurally sound. You have copper fill on all the layers to block EMI. You staple your vias, your power planes shut with vias. I'm not showing that happening on this board. I think I have those disabled. There's power planes on the inside layers here, and they're all blocked off with ground fill from every other power plane, and data lines have to run on their own planes so that they don't radiate. This is how we get by with not having the radio inside of a big milled aluminum case, which would block its EMI. We're just trying to do it on the board level because that's fairly light. So that was that. I have to find the other presentation. Where'd it go? Okay. So manufacturing costs. If you're trying to do low-cost satellite constructions, you're just doing the PCB layer. You're not doing big fancy cases. You're doing fairly inexpensive connectors. You're just soldering on little ribbon cables or just wires. These are some costs that I have kept track of from developing our own line of radios with just one other co-founder. Boards are about $3,000. All the test equipment was under $10,000. And assembly is $1,000 with 4-day turn time. And one thing I forgot to add here is the cost of the bill of materials of the radio, which is another $3,500 for this design for 16 units. It is fairly cheap to get started on hacking your own electronics in your own bedroom lab.
$3,000 each or $3,000 total?
For 16 boards.
Total.
So basically, one thing to note about PCBs getting done is that they have a minimum size that they run through the machine. So if you want 1 or you want 20, as long as you can fit 20 on one panel, it's about the same price. More or less, it's kind of the same thing. Once the machine is set up to do all the etching and the drilling, then they don't care how big it is. The electronics. Yeah, that was for all 16 also. Like, as an example, one 2.5 watt consumer S-band power amplifier is going to, and with 42% power added efficiency, I might add, which is really fantastic, which means you're dumping less heat and consuming less solar panel power. That thing costs $16 from DigiKey. If I was buying some sort of space-rated component, I don't even know. I haven't even gotten quotes. I mean, it would be $500, $600. I've seen ovenized crystals on sale at the CubeSat conference for over $1,000 for one crystal. I have 3 crystals on that design that I showed you guys, and the most expensive one was, I think, about $40 for a really, really nice low phase noise, like amazing RF characteristics, temperature compensated design. I'll go into that in a bit. I want to go through an interesting way that we're trying to solve one particular aspect of spacecraft design, which tends to be hard, which is radios. So because the FCC has split apart the spectrum and they have certain bands for certain types of operations for certain types of satellites, it probably means that there's nobody making an off-the-shelf radio that matches your application for your satellite, for your exact data rates, for your exact antenna, which is why people tend to end up commissioning these things semi-custom or fully custom from some third party. And so you're talking about paying for somebody's complete development cycle, paying a team of programmers to design a new packet protocol for you. If you are a company like L'Oreal that's been in the business for a long time and your satellites tend to be fairly similar from time to time, you can reduce a lot of these costs by buying the same kinds of things over and over again. But if you're trying to innovate and build new types of small satellites, you can't do that. So one thing that we're trying to do to solve that is to design an extremely modular radio system. So what I showed you guys there, that is a prototype model of the motherboard. But by using the same exact software front ends, I guess I can flip over to it. So on this design, you have your software front end with all of your data lines coming out and these MCUs on here, and they're all using one radio section, which means that you can only put out the same amount of wattage. I mean, you can debias your amplifier, but you're kind of limited to a certain range. You have a certain band that your low noise amplifier is optimized over, so you can pretty much only use this design over S-band. But by changing a lot of things, by taking the RF off of the motherboard and putting in drill holes instead with snap-on coaxial connectors, we can use the exact same software-defined front end and pop on Ka band modules, pop on Ku band modules, pop on X band modules. So if a particular person wants, say, I want 2 watts of C-band power for transmit and I'd like to receive at VHF, you just pop on those modules onto the exact same motherboard and they just sit into vias that you just solder them in or screw them on. You can almost instantaneously spin up radios spanning about, with this type of design, we're looking to span about 12 gigahertz of frequency range all the way from VHF up to Ku band. Everything is going to use high frequency connectors. It's not worth having the cost savings of using low frequency components because then you have to keep track of different types of inventory and you have to keep track of different types of boards. So everything uses Ku band design techniques and Ku band coplanar waveguide. And SMP are really, really nice board mount connectors that can pass up to 40 gigahertz in RF frequency, and they're really tiny and they have pretty good power handling characteristics. We are looking to reduce the cost of spacecraft radios for a semi-custom build, except the software front end, you can either recycle the same one or you can use a different one, down to about $6,000 starting from scratch to get the kind of radio you want, down from development cycles of paying some third party, $100,000 or whatever it is to design this for you by just having these different daughter boards and popping them on there. One thing that's pretty cool about our design is that we found this one chip. I won't tell you who it's from, kind of secret saucy, but it will just directly turn a digital signal into an RF signal up to a certain band. It'll just directly synthesize radio for you, and also do the same thing in the reverse direction. It'll take radio up to a certain frequency and turn it into bits on the back plane. And this thing just speaks high-speed LVDS lines on the back end, and you just plug them into an FPGA, which can then process and do everything digitally. That means that the whole front end that's mixing your signals up to KU band or whatever, none of your software cares about that. All it has to do is have some enable lines that turn things on and off, some ones and zeros here and there. But from the point of view of the software developer who's trying to design something for company A or company B, they don't care. It's all agnostic. It's the exact same thing that they've used before because the software stays the same. The other cool thing is the FPGA, they're a little bit more hard to program than something in C. They can take a little bit of time, but you need to run them in order to have data rates of about 100 megabit per second. But we're going to run this thing off of GNU radio, so the people who want to have lower data rates can just have their flight CPUs and their ground stations running GNU radio and sending information about the types of waveforms that it wants, simulating it in the CPU over to the radio. So the radio then doesn't have to do all of the synthesis of the waveform in FPGA, programming it in Verilog or VHDL or whatever it is that takes a long time. But again, once you have a few software routines, you can recycle them from design to design. So yeah. So you see how we're able to leverage off-the-shelf things. I'm saying words like FPGA. I'm saying words like analog devices. Yeah?
I don't know if this question is for now or later, but so why did they say X-band couldn't work, and how did you get around that impossibility?
Well, by not knowing about it.
Well, yeah.
Things, okay, so X-band, we're talking the range of frequencies around 8 to about 10 gigahertz, right? So that is like your phone, the highest frequency that your phone's worked at for the longest period of time was L-band. And then, so that's like, I don't know, 1.4 gigahertz or wherever it is that the cell phone bands were. And then they added the Wi-Fi chips to phones. So now phones could talk at 2.4 gigahertz. So what happened when we added Wi-Fi as a global standard is that everybody started making inexpensive chips for S-band. So now 2.4 gigahertz, which is still like a lot of oscillations per second. You're talking, you know, the electrons in your line or the photons in space are flipping back and forth at gigahertz. Like, that is really high, but we don't think of it as high anymore because it's just become a standard. And so I promise I'm getting to you're answering your question. I'm just going through a bit of history to punctuate it. So companies with the smartest of people, analog and linear, they've all thrown their best engineers. This all happened like 15 years ago. Like, this isn't like, you know, right now people aren't going, wee, Wi-Fi. You know, this already happened. It came in and went. Well, not went, but we're going over to the 5 gigahertz band soon. Anyway, so they made that band inexpensive. That means connectors for that band, amplifiers for that band, circuit design techniques are all known. You go to that company's website and they will have complete evaluation kits for the correct design of a radio. And guess what? If it's a good design for Earth with minor modifications, it will work in space. The things I went over before. And then recently, the 5 gigahertz ISM band became in use. So now modern, you know, iPads and everything, they speak WiMAX. They speak at almost 6 gigahertz. So you're getting really, really close to X-band now. And again, over the last 5 years, companies have been making amplifiers, design techniques, transceiver modules, direct synthesis units and receivers, and forward error correction codes, and the whole software suite that is good for that band. So at the time that we were trying to do this, like that had already happened, but nobody was yet doing really inexpensive stuff at X-band. So probably the person who told my boss that at whatever conference it was, he was maybe just about 5 years out of date and hadn't realized how much people had pushed forward into 6 gigs. Because guess what? Once you have 6 gigahertz components with minor tweaks or by finding sister units, you can make 8 gigahertz components. So it's by riding on the coattails of what industry is doing already is what made inexpensive small radios possible at high frequencies in a CubeSat. I doubt it could have really been done about 20 years ago, but we were in a sweet spot where it was possible. And same thing goes for this new design I'm doing as part of BitBeam Technologies. It is, again, leveraging chips. A lot of them have come out in the last year. So again, the same design would not have been possible 3 years ago. That also means that, yeah, you have a bigger testing burden. You have to do environmental testing, radiation, because these are brand new cutting edge components. You know, God only knows if they're going to work up there, but you can test. And you can save a lot of money by using them. Did that answer your question? Good.
Is that mostly silicon-based stuff nowadays, or is it gallium arsenide?
Yeah, gallium, a lot of it, yeah. The higher power efficiency stuff, absolutely. The MCUs and stuff are not, but the power amplifiers, yeah. But even if you don't want to start your own space company or you don't want to innovate in that field, there are other ways to explore space. Like there's hobby space. You can start talking to radios that are already up there. There's a million CubeSats up there that have open radio formats. So you can either just listen to packets coming down from their satellite and figure out what's happening. Maybe they'll have some temperature data. Maybe they'll have some pressure sensors. You can, for example, listen to the ISS's beacon. And these are mostly at the amateur frequencies, like 437 megahertz. And all you need is a rotor set, a couple of Yagi antennas. This is a picture from University of Strasbourg. I don't know how to pronounce them. I was not involved with this at all, and I didn't build this one, but I built a lot like it. So I'm just using their picture because it was a nice picture on the internet. You can put together one of these ground stations and start tracking your satellites almost immediately. In about less than a week after ordering the parts and calibrating, putting everything together, you can be talking to stuff in space. So that's a fun way to get into the field also. But
Are you talking or just listening?
So I'm not sure if right now in this instant there's any satellites you can talk to. You can listen. I know that there's one going up in August that I have a radio writing on. We're going to release the code open source, and so people can ping the satellite. They won't be able to send commands all the way through because that part's going to be encrypted, so there's no way they can get out of the radio and to the flight computer, but they can at least get to the radio and say, they can poke it. Go, hey, tell me something. What's your temperature? Like there's a temperature sensor on the board, and so you can get that kind of information out of it. So I know that'll be available in August, and that'll be an S-band unit. And so again, a dish on the ground and a set of Yagis in a quiet area where there's not a lot of Wi-Fi interference, and you should be able to talk to the satellite. Yeah. So basically, the whole thesis here is you ride on the coattails of what people are moving into already. One or two people, a small startup, you can't invent a whole new field. Well, sometimes you can, but maybe I'm not that smart. But I am smart enough to use components and trends that other people have done and just hook on to that. So when I see that Analog Devices has released a new chip, I'm always on I'm subscribed to all of the chip manufacturers' mailing lists, and I go, how can I use that? Or maybe they've dropped the cost of a design, and so I start utilizing that. This kind of stuff works in space. You can use the schematics that they give you on their website, change out the oscillators for temperature compensated designs, shield everything excessively, because if you jam your satellite's receive channels with your transmit lines or with your data relays, you will never be able to reach your satellite. Put in really good software protocols so that you can't accidentally mess up the image that the radios are running. Put your receivers always in a safe state. Have them always be on and always listening at a low data rate. If you want to talk to it at a high data rate later, fine. You can tell it to go over temporarily to a higher data rate or higher performance modulation scheme, but have it default to something slow and reliable that you can reach it from just a set of Yagis. What else? We've gone through temperature. Use leaded solder to prevent whiskering. Use low loss PCBs, so the top layer where your actual RF signals are running. Let me go back to this really quick. So these copper traces right here are coplanar waveguide. That's a way to contain the electric fields nicely to prevent EMI and also to have low loss and 50 ohm lines. They are basically seeing the ground field that's on the top of the board, and they're seeing the ground that's between the top and the second layer of your PCB stack. And you need to make sure the dielectric that's in there is a low loss material. Rogers 4000 series is really great. It increases the cost of your boards, but again, you can still get 16 boards come back and under $3,000 even using that. Do copper fills everywhere, a lot of vias. You want to have mounting holes for heat spreaders, because up there fans will not work because there is no air. And so here you can see these bolt holes are mounting holes for an aluminum plate to go underneath. Aluminium is not as conductive as copper, so you might think, well, why would you want to use aluminium instead of copper as a heat spreader? Because down here we might use copper for something high performance. And it turns out copper is a lot denser, and so aluminium is still a better choice because you'd rather pay a little bit of volume to prevent the huge mass hit. So you just use a little bit more of it. And heat straps to the chassis, and make sure that wherever that heat strap is going, or the chassis of your spacecraft is facing enough towards the cold part of outer space, so it can radiate heat effectively. It's not going to radiate heat very effectively towards the Earth or towards the sun, but it'll cast it out the rear end that's pointing towards the cold stars. So by using all that kind of stuff and keeping in mind, you can right now start designing electronics that will be used in space. And with good probability, they will work. You have to be responsible about how you do it, make sure you get the right licenses. And make sure you can always maintain control over your satellite so that in case it's about to go into contact with somebody else, you can help avoid that collision. I see this recent trend of these little postage stamp size satellites that people are really thrilled to assemble. I'm not actually sure that's very ethically good in space, because these little postage stamps, they're almost untraceable. They're just scattered around like dust, and people can't control them or even reliably talk to them, and they're just causing space debris. But in the next size up, as long as you can control and command your satellite, I think it's a great field to innovate in. And I'm done, so let's do questions.
So what happens when things do collide?
You get a lot more pieces. And
do people
are they still
do
in
people
orbit?
get like in trouble with big fines, or?
I don't know.
Yeah.
So do you know the answer to that?
No, but did you see the movie Gravity? That's what happened.
So you guys have your hands clean. You haven't caused any big international incidents.
Yeah,
We can talk offline.
We did, but nobody knows who. Mostly not.
One really quick thing for that question, and then I'll get to that. Every single object that then emanates as a new traceable piece of debris, and again, I think the Air Force or whoever it is, whatever government agency has the radars, they can trace everything that's, I don't know, bigger than a couple of postage stamps. I don't know if we're talking 2 inches or 5 inches across, but like, that small. Anything bigger than that gets cataloged. It gets a catalog ID. It gets posted to their website, and it has a 3-line element assigned to it, a TLE, that anybody then with a ground station can use that TLE, plug it into a propagation program, figure out where and when it's going to be there. And so that means that every object then after this collision gets tagged, and they're using all of those objects to predict future collisions.
I know the Air Force is really sweating getting to some smaller sizes too right now.
Because the smaller debris can cause bigger pieces to fall off of things.
Bigger pieces become smaller pieces.
Exactly.
I'm thinking if you launch a bowling ball into medium Earth orbit, it's going to be there forever. But you're mostly going into low Earth orbit, where there is a little bit of drag, and the life expectancy of a satellite varies with its mass to drag ratio. I would think
5 years in our playing field.
in that sense, I would think that a small postage stamp-like thing might flutter and drag and re-enter a whole lot more quickly than what people are normally watching out for.
That is correct. So small, extremely small satellites, including these postage stamp things, they will re-enter quite quickly, and so they're not a dangerous thing to stay up forever. it's that amount of, remember the numbers many slides back showing the amount of kinetic energy and potential energy you have to deliver per kilogram to get up there. Well, the drag forces are proportional to your cross-section, your drag cross-section. So if you have a long, skinny, extremely heavy satellite, and you can always keep it so that its cross-section is just the front of the cross-section of the skinny side, it's going to be up there for a long time. If you have like a big sheet or something and you rotate it so that the whole sheet is a sail against all the particles up there, it's going to re-enter really quickly.
What about software for communications and robotics, and also for re-entry as well too? Guys look at those?
Yeah, so software for robotics.
Real time. You want to do something like manipulation of something.
Oh, okay.
Yeah. I mean, that's
Let's see. We have done some tests, I'd say, that qualify as that. Okay, so I can speak generally about that. Having not built an exact robot with grasping things, but satellites are kind of robots.
Yeah, that's where the zero-G questions come
in. So the software protocols to command your satellite, you want things like important data to continue to be sent until it is acknowledged. You need to have the appropriate data rate for the links so that you can get enough data back so that you can give intelligent commands up to your satellite. So if you need to crank up your data rates of your radio links to get a lot of telemetry if you're doing some big active manipulation, then you have to do that. You need to support that link. A lot of times for really, really fast stuff, the ground can't actually command the satellite fast enough to do stuff. At SpaceX, for the rockets, they were fairly self-sustained. And most of these things are making decisions on their own for a lot of things, just like fighter jets. Like the person kind of tells the fighter jet to point left, but it's the computer over there that's doing all the fast control loops and actually, figuring out how much, force to allocate to every thruster. Same thing with satellites. They have to have a lot of built-in knowledge, and rockets also, in order to be fairly self-sustained. You just kind of point them in the general right direction, but you often can't reach them fast enough with the huge latencies in order to tell them what to do on a minute by minute level. It's going to be an interesting thing when we're going to have like robot grasping arms that we're going to want to control from the Earth, and we're going to have to deal with that propagation time when we're telling the robot arm what to do. I'm not sure of a good way to get around special relativity there. You're kind of limited.
They're doing Robonaut right now on the ISS. I don't know where that stands, though.
They're probably controlling it locally from the ISS.
I think they're doing both. What about also re-entry, the issue of you want to return something from your nanosat, as an example. So a friend of mine did the SpaceX heat shield, as an example, but have you guys looked at control software for re-entries and things like that?
Yeah, so to re-enter you want to increase your drag, and so you want to be able to control, so you can do it two ways. You can either reduce your velocity, so if you have some sort of active thruster, you can either do a plasma thruster, or you can do an actual can of some sort of compressed gas, either flammable or non-flammable. You can fire in the wrong direction, opposite to the direction you're going, and you can drop down fairly quickly, or you can rotate your satellite by playing with your position, by just rotating yourself around, and you can do that by playing with magnetic fields, by pushing off of them, by basically having coils in different directions, and you just kind of nudge yourself into a different orientation.
What are you guys working on?
Various companies are, yeah. Yes?
I was wondering the more general case, the early CubeSats I knew about, they kind of tumbled and did what they would, and there wasn't a whole lot of attitude control, and there wasn't a whole lot of thrust available to it. How far has that advanced? What you mentioned making sure your heat radiators were pointing to the cold stars. How much control do you have, and how is that done? And if you are on a collision course with another satellite, how much control do you have to, what do you do with that information?
In terms of, the first question is, how do you maintain correct pointing of a small satellite? And you need to do the analysis of your moment So how much mass you have far away from your center, and that tells you how much force you need to exert in order to rotate around all your various axes. A common technology that's used there, there's two different ones. One are plasma thrusters, and the other ones are magnetorquers. There are off-the-shelf components being sold at all of the nano satellite conferences, like at SmallSat in Utah this year. You can just get these things. They're not cheap, but you can just buy them and pop them into your satellite, and you need, enough to make sure you can rotate over every axis. You also can store up energy by spinning up something on the inside, and then depower the spinning thing by using energy off of your solar panels. So that was the first question, how you maintain pointing. The second one was avoiding collisions.
How much delta V can you
Right. I don't know exactly how much delta V you can give. I haven't done the analysis, not being a GNC engineer myself. I mostly focus on the radios, but I do know that you get notification from the Air Force a long time in advance, typically. It's like your first email about the imminent collision will be something a week out. And of course, in a week, a lot of things change. And if you actually take action immediately, a very, very small amount of delta V is enough to just completely change your cones in opposite directions. So if either or the other party just does a little bit of a zap with a plasma thruster or just increases their drag a little bit, they will get out of danger. Of course, they're
Little 1-inch firecrackers on the outside.
You could. You could. I don't recommend that particular design, but I think physically it should work. Yeah.
Okay, actually, he raised a second question, which was, you've added some delta V, so now you've changed your triplet, whatever it's called, and now you're aimed towards somebody else. How dense is it?
Up there?
Yeah.
Let's see. You'll get a couple of notifications a year for one satellite in a couple of years, maybe one or two.
Which way to go to try and to minimize the chance that you're not hitting him, but you're hitting him instead. Yeah.
You know, I don't know what the mental process is. So the question was, you're on an imminent collision course with person A, but how do you make sure that you don't change your course and hit 5 other people who are also sharing an orbit with you? I'm not sure how you would do that. You probably would stay in your orbit, more or less. You would just go a little bit forward or back along it. So basically, by just increasing your velocity a little bit, you can just increase the altitude of your orbit just a little bit, and mostly just kind of stay in the same direction. You probably don't want to change your course completely and go sideways, A, because your business model probably isn't for that other orbit. You probably put your satellite where you wanted it, and so you just changed it a little bit. I don't know if I've never seen in the emails the Air Force gives you any sort of planned maneuver, but you'd probably just get on your computer, you'd run the 3-line elements for you and everybody else of interest. Most importantly, obviously, the station, which actually has people in it. That's your most important consideration to make sure you don't go into that orbit directly. And plan out a new route.
You mentioned business models. Other than remote sensing, what is the business model?
Communications. There is an interesting project. It's all public. It's on their website. I can pull it up. Called, for example, OuterNet. Let's do a Google search for that. I can't connect to the internet. Oh well. I guess the Wi-Fi doesn't work down here. They're trying to do free media from space, like Wikipedia and things like that for countries which may have blocked access to that. So that's kind of a not-for-profit model of somebody who's trying to do something cool in that space. You have Planet Labs, which is during Earth observation. So actual high cadence, very, very low latency images of the Earth. So in case something interesting happens, you can actually just check the photographs that were taken 5 or 6 hours, maybe at most 24 hours ago of that region, versus like Landsat and other imaging satellites of maybe 10 or 15 years ago. You had to call up the company or get an RFQ on their website, and you issue a check for $40,000 or however much it costs, and they plan it, and on the next satellite pass, they will slew their entire satellite and take an amazing, immaculate, extremely high-resolution shot of that exact teeny tiny space that you wanted. But it's certainly not the whole world being updated on a daily basis. So communications, observation, ship tracking, airplane tracking. You can do a lot with sensing weather. Weather satellites are also, the US ran out of funding to replace the 2 weather satellites that it has doing North America right now, so we're just gonna kind of be without weather coverage in a couple of years. In California we'll be okay, but I was in Alaska recently and those people are like freaking out. They're like, people are gonna start dying in Alaska. You know, somebody who drove out to do some winter fishing in a pond without that, you know, low latency weather data for Alaska, people are just gonna freeze in their trucks. And so that's another thing that we can get in and is replace those weather satellites with small, agile spacecraft. And there's more.
This might get you way off track, so maybe you'd rather defer until after the camera turns off. But
Yeah.
in your biography on the class website, you mentioned standing on the deck of a ship in the Pacific catching bits coming down from a falling satellite.
Yes.
It's impossible not to wonder what that's all about.
Yeah, so this was Falcon 1 Flight 4 for SpaceX. We had never had a successful launch before, but they placed a couple of us on a flat-bottomed military barge. So she's like a container ship. She's got a big bridge and like a big flat end with a crane, and you can lift stuff conveniently, like maybe a rocket chassis that comes back. And they sent us out to, so you have Kwajalein is like down here near Indonesia somewhere. You have Hawaii up here, and you have California over here. And so the rocket was going to launch this way. And it's got your different stages and the front end with the payload in it. They had us motor out in a boat into the middle of the Pacific Ocean. So here we are with our little flat-bottom military barge. And there was an impact zone somewhere in the Pacific Ocean. And this impact zone was this huge compromise between the Kwajalein range services and SpaceX. We had our own analysis that said, well, the impact is going to be right here. And they said, well, no, but our analysis shows it's going to be right here. And so a lot of hemming and hawing and back and forthing. We were placed somewhere outside of some compromise of those 2 boxes, but just outside. Yeah, you want to be fairly close so you can get the data as it's streamed down, but not so close that you have a probability of being hit. So anyway, so the barge parked itself outside of this big expected impact zone, and there was stage separation that happened over that. So these 2, this one shuts off its ignition. They separate. These 2 continue on, so the second stage and the fairing, they continue on to orbit. And this thing starts falling in a parabolic arc. And Elon is all about doing recyclable components. And so we were trying to get data from that first stage to see how it would do. I can't tell you anything about the results or really anything else except that we had a dish and we were pointing it at the satellite and we were getting the radio link. Yeah.
More than 6 degrees.
You say, wait, that one's not ours.
We could see it with the bare eye, just barely, but we could see it in the distance. But we had practiced it a lot, and there was more complex stuff going on than just by hand. But I can't tell you what the technology we used was, obviously. But yeah, we basically just pointed the dish at the rocket as it went by, and we got data from it, and then able to analyze it later.
When you talked about the postage stamp guys, how are they getting deployed? Do they just jam a bunch of them into one of these pea pods and just spray them out, or
That's a good question. I don't know how the postage stamps
tape
are being
them to the
deployed.
outside of-
I have no idea. I
they
think
are
it's
out
some
there.
sort of fairly open source project or some sort of open collaboration, so you should be able to find it on the internet, figure out how they're doing that. Obviously, getting up to orbit is fairly cheap because their weight is nothing. You know, they're like maybe an ounce or 2. So, yeah, I don't know what the deployment is like.
Hopefully it's good.
Yeah. My name is Helen Lurie, and I design radios and electronics for a really tiny spacecraft. And, huh? What?
How tiny is tiny?
Oh, how tiny. Well, you're basically limited by some aspect of responsibility to other people in space, which is as long as you can be power positive and can control your satellite enough to avoid collisions, you can make it arbitrarily small aside from that, as long as those constraints are met. I typically work in what's called the CubeSat environment, which is about 30 centimeters by 10 by 10. And then unfurlable solar panels will make it more like a meter across. But in package form, it's about a bread box, smaller. Okay, so why space? It's got a really good location, and location is everything here. There's a lot of applications. For geo, you do broadcast, because broadcasting radio signals from space is actually cheaper than digging up all the dirt in Canada and running fiber all across all that lone tundra all over the place. So instead, you just put one GeoBird up, which is kind of crazy. Think about it, that $1 billion is cheaper than that. But yeah, digging dirt is really expensive. Internet for ships, the Arctic, MEO, it's a little bit closer. I'll have a plot of the distances from the Earth, but that's medium Earth orbit. It's a little bit below GEO. Again, you still do communications from that. You can do space physics, and the GPS satellites are up there, which we all use. And LEO is mostly the playground where I play in. And there's a lot of things about LEO that make it easier to start innovating in it and to start doing low-cost manufacturing techniques that you can't quite get away with in GEO. Again, communications, spying on people on the Earth. I don't work for any sort of military, so I don't spy on people. Earth exploration, ship tracking, plane tracking, like the recent Malaysia airplane that went down. There were satellites that were listening to those signals, for example. Laser comms research, photography. So this is a little bit small to see, but I think we can do this. Do you see the Earth? And right next to it is the little blue line. That's where LEO is. So it's really, really close to Earth. And then green is MEO.
You want a pointer?
No, I think we can just do colors. And GEO, or if you have one, I can do it. That might help. No, you don't have it? Okay, that's fine. I can just point and just flail my hands wildly at the screen. Ah, schmancy. Thank you. Oh, let's see. Ah, look at that. Okay, and GEO is really, really far away. It's actually off this chart a little bit. It's 35,000 kilometers away. So being up there, there's a lot of constraints, like the space environment. Stuff is really, really far away. So there's signal latency issues. So normal TCP/IP won't work if you're trying to connect up to your satellite because one side is waiting for an ACK and the other side hasn't even gotten the packet yet before you time out. The other big thing is, like, you have no physical access to it. So if you push a software bootload to your satellite and it causes the default state of your satellite to go into like a non-listening mode, you have lost contact and you will never regain contact again. You cannot send an intern to go flip switch in the server. So whatever you do, whenever you do a design technique, you always have to have a safe state that the satellite will go back to if it hasn't heard from anybody in a while. Vacuum. You get things like multipaction. Fans don't work well for cooling. It's like everything's covered in a down blanket. And solder whiskering. So multipaction is kind of a fun thing. We don't really run into it in LEO, but when you have a big waveguide and you have photons or electric fields, however you want to think about the universe, going down this thing. If there are certain power levels that are strong enough and the frequencies of oscillation of the signals match up with the dimensions of the waveguide just right, then as the electric field energizes electrons on the top side of the waveguide and causes them to shoot out, they'll reach the bottom just about the time that the potential energy is flipped the other way. These electrons get ejected also. So you get this rising wave of electrons going back and forth and welding the waveguide shut or damaging it in some way. If any of the conditions are not met, like your signal's not strong enough or your waveguide's not quite the right size for this to happen, it won't. We don't have to worry about this in Leo because we don't tend to run like 60-watt traveling wave tube amplifiers like they do at Laurel. So what else? You always want to use leaded solder. It's a little bit better for a lot of things. Solder won't whisker as much if it's got lead in it. And so this actually runs into using off-the-shelf chips because they all tend to be COTS compliant. Not COTS, or COHT, whatever the lead compliance. Temperature changes. Your satellite will go through -25 to +50 degrees, and this depends on your orbit, this depends on the time of year, this depends on your size. But in Leo, we see these kinds of temperatures. In Geo, they can be more extreme. Practical thing is you want to use TCXOs, temperature compensated crystal oscillators, instead of just an oscillator for your clock. A geostationary satellite, we use an ovenized crystal. So that's like a big box that's constantly keeping the entire crystal at warmer than it would ever get to naturally, and so it can always keep it from getting colder. There's a lot of problems with using ovenized crystals. First of all, they tend to be like this big, or you can get them a little bit smaller. And the other thing is they take a long time to warm up, and while they're actively warming, the crystal's frequency is drifting all over the place, and so that means your radio center frequency is drifting all over the place. So that means you have to keep them on all the time. In Leo, we can't afford the power. So we cut corners. This is the first corner we're cutting, TCXOs, and they're good enough, and they're not too expensive. You want to test everything in a thermal oven, so you cycle it, preferably a thermal vacuum oven, so that your spacecraft will actually experience the vacuum, and so heat buildup will happen as expected. Debris. Occasionally your satellite runs into things at 3 kilometers per second, or your satellite will either its fault or somebody else's fault. Maybe it's a piece of debris. Maybe your satellite's lost control. You tend to sign up for these Air Force email announcements. There's a government entity that tracks every single object bigger than, like, I don't know, a postage stamp or a couple of postage stamps up there. And you'll get these email alerts, and I've gotten them a few times. They're quite worrisome, like, you know, dear so-and-so, you are registered as an administrator of object da-da-da-da-da. You know, you are imminent for an upcoming collision in, 1 week with this other object. And so then you get on the phones and you start scrambling, calling the other operator and seeing who's going to steer out of the way if it's looking like it's still going to happen. So there's a lot of radiation up there also, and particles flying all over the place. Leo is a lot easier than Geo. You tend to be protected very strongly. You're closer to the Earth, and you have convenient magnetic fields that are deflecting a lot of crap that you don't want hitting your electronics. And so we can cut corners because we're closer to Earth that you can't do in Geo. So some parts of this talk are not exactly applicable to doing low-cost engineering up there. There's a lot of regulations, ITU, NOAA, FCC, everybody wants a piece of the pie. So NOAA cares about debris. So if your satellite, when it breaks apart upon reentry, is going to actually hit with a big chunk somebody, you need to register that. Basically, you need to get a license showing that your satellite will burn up, that you've done the analysis as you're going through the atmosphere. The FCC, they care about frequency allocation. If everybody just grabbed however much bandwidth or frequency they wanted all the